Hello AP students, welcome to Unit 2. So in this unit we're really going to focus on vectors, and if you remember, a vector is something that has both a magnitude with is how much, and a direction, which is the which way. So what kind of things did we deal with last unit that had that were vectors? Well, we had displacement. Displacement was the magnitude was how far you ended up away from where you started, and the direction was which way. We also had velocity, and velocity is how fast you were moving, and the direction was which way, strangely enough. We also had acceleration, which is the rate at which your velocity is changing, and the direction was which way. And there's one more that we'll deal with pretty commonly, and that is forces. Forces have a magnitude, which is how hard the object is being pushed or pulled, and the direction is, simply enough, which way. So that should make sense. There's different ways we can represent vectors. We can use words: 2 meters east, 4 meters west. We can use a little bit more mathematical terminology and say our delta x, or displacement, was plus 2 meters, or our delta x was minus 4 meters for the west. Or we can use graphics, in other words, a picture. And our picture will be very simply just an arrowhead, and we'll use that pretty commonly. If we completely rely on the picture, we have to come up with a scale for our vector lengths, because the length of the arrow represents the magnitude of the vector, and the arrowhead points in the direction of the vector. We will not do this a whole lot with a scale. There's a little bit on the first page of that worksheet, but for the most part, we're going to use sine, cosine, tangent, and Pythagorean theorem. That will get us where we need to go. But we're going to start off kind of looking at it with graphics. A vector has two components. It's the how much and the which way. Moving that vector on the page or redrawing it doesn't change anything about that vector. All it does is change where it's starting and where it's ending. It doesn't actually change the how much or the which way, as long as you draw it with the same length. And we'll need to move vectors around in order to add them. And just like normal numbers can be added, 3 plus 5 equals 8. Vectors can also be added, but they're not necessarily as simple, because you have to take into account the direction. So 3 meters plus 5 meters doesn't always mean that you're going to end up 8 meters away from where you started, depending on the direction that you went in both cases. So this is how you add vectors graphically. You just simply put them tip to tail. So tip to tail, tip to tail, tip to tail. And then you can't, touch arrowheads or touch tails. That would be poor form for adding. When you do these, when you add vectors, 3 meters plus 2 meters plus 5 meters equals whatever meters, the answer, the sum, is called the resultant when we're talking about vectors. So the vector sum is called the resultant. And it's just the result of drawing the vectors tip to tail, although we will analyze this more mathematically. So if we look at a displacement, two displacement vectors, and if we walk 2 meters to the right, and then we walk another 3 meters to the right, if we add those together, we just get 5 meters to the right. The resultant, the vector sum, is 5 meters to the right. And notice again, we put the vectors tip to tail. Okay. Now, if I walk 2 meters to the right and then 3 meters to the left, okay, this is where 2 plus 3 doesn't always equal 5, I'm not going to end up 5 meters away from where I started. I'm going to end up with a resultant of 1 meter to the left, so that's my resultant. Notice I kind of put these tip to tail, but I didn't, so that you could still see the original blue vector. So the resultant is, again, from start to finish. It's from the starting vector to the ending vector, which, again, I didn't put these directly on top of each other just so you could still see the vector, but the resultant is 1 meter to the left. If we were to talk about signs here, and we were to add these vectors mathematically, the 2 meters would be positive, and the 3 meters would be negative, because going back to the last unit, remember, our standard Cartesian coordinates puts to the right positive and to the left is negative. And when we add those, we're going to get -1. And that negative means that our resultant was to the left. You can add vectors. It doesn't have to just be with displacement. You can add velocity vectors, and you can add any vectors for that matter. So let's say that we were at the airport and they had one of those people conveyor belts that they have at the airport where you can stand or you can walk, but it's always more fun to walk because that way it adds your velocity to the conveyor belts. And that's exactly what we're talking about. Let's say that you're walking 1 meter per second north and you've got a conveyor belt that's moving at 2 meters per second north. If you were to walk on that conveyor belt and add your velocity vectors, you would have a resultant of 3 meters per second to the north. So here's my amazing graphics, I tell you. So there's the person walking 1 meter per second relative to the conveyor belt. So we have to kind of keep an eye on what we're talking about the velocity to. Remember, velocity is always relative to something. We can't ever say that something is moving at a certain speed. It's always moving at a speed relative to something else. So when we say a person's velocity is 1 meter per second, in the example before we said it was moving relative to the walkway. And we said that the walkway's velocity has a velocity of 2 meters per second. We meant that it was moving at 2 meters per second relative to the ground. So when the person was walking on the conveyor belt, they had a velocity of 3 meters per second relative to the ground. Now, if we flip a switch on the conveyor belt and make it move the other way, and the person walks 1 meter per second north relative to the conveyor belt, and the walkway moves at 2 meters per second south, which we're going to make negative, okay, relative to the ground. When we add these two vectors, we get a resultant of -1 meter per second, or 1 meter per second south. Here I put them on top of each other so you could see the resultant is from start to finish. The resultant is always the arrow drawn from the start of the arrows to the finish of the arrowheads. There's a really cool Mythbusters episode where they add velocity vectors by taking a tennis ball or I don't know what it is. It's like a dodgeball or a volleyball or soccer ball. It's one of those. Let's say it's a soccer ball. And they drive a truck at, let's say, 30 miles per hour, and then they shoot the soccer ball out of the back of the truck at 30 miles per hour. And they get those velocities to add 30 meters per second to the right and 30 meters per second to the left. And that's like adding +30 and -30 and getting 0. And what ends up happening is that ball just simply drops. It doesn't move left or right. It just simply falls down because of gravity. It's a pretty cool episode. Again, we can use velocity vectors if we have a plane that can move at 100 kilometers per hour relative to the wind, and the wind moves at 25 kilometers per hour south relative to the ground. Then the plane is going to be moving at 125 kilometers per hour relative to the ground. And this is something that's important when it comes to vectors. The order of addition does not matter. If I add my A vector and my B vector, if I put them tip to tail and draw my resultant from start to finish, okay, the resultant vector is always from start to finish, I get a certain resultant. If I add B plus A, I'm going to get the same resultant. This is basically like saying, 1 plus 2 equals 2 plus 1. So there's nothing too surprising about that, except it's good to see it in a picture form. This also works if you're adding negative vectors. It doesn't matter. A plus B, where my resultant is from A to B. And if I go B plus A, if I do the B first and then the A, okay, I end up at the same location, start to finish. I end up at the finish line. So the key thing here is it doesn't matter. A plus B equals B plus A. Okay. When you can also subtract vectors, and this is not hard. In order to subtract vectors, you simply flip the vector that you're subtracting. Okay, the vector that comes second. So 2 minus 3 means we flip the 3. So instead of subtracting 3 meters to the right, I'm adding 3 meters to the left. Okay, so and that's just saying 2 minus 3 equals 2 plus minus 3. Okay, 2 minus 3 equals 2 plus minus 3. It's the same thing. Okay, now, if I have 3 meters minus 3 meters to the left, 3 meters to the right minus 3 meters to the left, remember what we do is we flip the vector that we're subtracting off of, and that's the one that comes second. And we would end up with 3 meters to the right plus 3 meters to the right. Again, all we did was flip that vector. Okay, so you can add vectors. They don't all have to be in this x direction or the y direction. You can mix x and y directions when you add them, but again, you've got to take into account direction. That's important when we deal with vectors. So remember, all you do to add vectors is you put them tip to tail, and the resultant is the vector that goes from start to finish. And notice I tip to tail, and I went from start to finish, and that's my vector sum in this case. Now it's at an angle, which is fine. We just have to deal with the angle using a little bit of trig. So here I did 2 plus 3. Remember, I can also do 3 plus 2 and get the exact same answer. Okay, 2 plus 3, 3 plus 2 gives me the same resultant. Okay, so 2 plus 3 is equal to the resultant. The resultant is equivalent to the addition of those two vectors. So basically, that's like saying if I walk 2 meters east and 3 meters north, I'd end up in exactly the same position as if I had walked the path of the red resultant. I'd end up in exactly the same place. Okay, so did I add the vectors on the left here? Did I add these vectors properly? Did I put them tip to tail? Yep, that looks good. Okay. Did I add the vectors in the middle properly? I put them tip to tail. Yep, that's good. Did I add the vectors on the right properly? No, I did not. I put them tail to tail, and that is not it does not work. And anyway, since you go from start to finish to draw the resultant, where would you? I guess I see where you'd start, but where would you finish? So it just doesn't make any sense. Okay, so here A, B, and C, and there's different ways I can add them. Did I add the vectors properly in box 1? I think so. Box 2? I think so. Box 3? I don't think so. Okay, and notice that I ended up with the same resultant for box 1 and box 2. Let's see, what would I have ended up with? Where would I have drawn my resultant from in box 3? I guess I could have started here, but where would I have finished? Over here, I guess. That would not be right. Let's see. So let's look at box 4. Did I add my vectors properly here? I did not. What about box 5? I did. And box 6, I did not, because I have tail to tail and tip to tip. Okay. Again, notice the resultant for each one of these is identical. Anytime I add them properly, the resultant will be identical. Okay, we've already drawn that. Oh, notice, it doesn't matter. Notice that if I add A plus B or B plus A, I get the same resultant. And if you do that on both cases, you end up with a parallelogram. So this is another way you can add vectors, is you putting them into a parallelogram and then adding them. We will not be dealing much with that method.